So today we're going to start talking about Border Gateway Protocol, and we haven't really got into this before, so this is something quite new. So we're going to get into this and take a look at how this particular protocol works. So we're going to look at describing BGP and its basic operations. We will name and describe common BGP attributes, list the steps in the BGP route selection algorithm, describe BGP peering options and the default route advertisement rules, and configure and monitor BGP. So let's have a look at an overview of BGP to begin with. So what we find is BGP is the core routing protocol of the internet. So it is the internet's routing protocol. Now, let's just have a bit of a think about the type of routing protocol that it is. It is an exterior gateway protocol. So up until now, the protocols that we've looked at have not been exterior gateway protocols. They've all been IGPs. Okay, so what I want to do to begin with is for us to think about and to get an appreciation of the primary difference between BGP, which is an exterior gateway protocol, and the IGPs that we've been looking at so far. So let's begin with thinking about what an IGP does. First of all, give me some examples of an IGP. What is the name of some IGPs that we have looked at to date? Can anybody name? OSPF. Yeah, OSPF is an IGP. So, and there are others, of course. Looked at RIP, we've looked at EIGRP, and we've mentioned ISIS. So let's just think about OSPF, for example. Now, I've got a network on which I go and configure OSPF on my routers. Now, what is OSPF going to do? So first of all, one of the first things that it does is it automatically finds other routers that I configure with OSPF. That is an automatic mechanism. So I configure, just say, I don't know, I've got 50 routers. I configure them with OSPF. Okay, those 50 routers automatically are going to start looking for the other routers that are also speaking OSPF language, if you like. Okay, they're also configured with OSPF. They're going to find them. They're going to establish a neighbor relationship with them, aren't they? That's going to happen, right? This is automatic. They are going to see if they need to establish an adjacency. They will certainly establish adjacencies with at least the designated router and the backup designated router if we've got a multi-access network, or if we've got peer-to-peer links between our routers, then they're going to establish adjacencies with all those routers. And this is going to happen automatically. Now, this is exactly what I want to happen automatically. Not only are they going to do that, then they're going to start sharing link state advertisements. So they're going to start sharing information between those routers about the network, about the state of their links, the networks that their links are attached to. And then what's going to happen next is all of those routers are going to start calculating routes throughout that entire topology. And all this is going to happen automatically as soon as I have set up OSPF on those routers. So there is an automatic discovery process, there's an automatic adjacency formation process, there is an automatic exchange of information between those routers, there is this free exchange of information that results in a complete establishment of connectivity throughout my autonomous system. And that's exactly what I want to happen. Now let's take a look at BGP. So we've got in this diagram here a few BGP routers within these autonomous systems. So do these routers automatically start looking around for other BGP routers, find them, start communicating with each other, establish these kind of relationships, these neighbor type relationships, and start sharing routing information? Does that happen automatically all over the internet? Well, no, absolutely not. That's not how BGP works. In fact, BGP works quite differently. And there's a few reasons for that. First of all, these autonomous systems are often separate commercial entities as well. Okay, so for example, I might have our local ISP down the road here, and they might be one of those autonomous systems. Well, my local ISP is certainly an autonomous system. There may be another ISP. Let's just say we've got a tier 1 ISP here in Australia. Say Telstra, for example, is a tier 1 ISP. And they would certainly have BGP configured within their networks. Do I want necessarily those two autonomous systems to start communicating with each other, start building routes to each other, start sharing traffic and having traffic flowing between each other just automatically? No, I don't. Because they are two totally separate commercial entities. Okay, and so when it comes to the BGP, the establishment of a neighbor relationship, which we call a peer in BGP, a peer relationship, is always done manually. So every peer with every other BGP router is established by the network administrator. And the reason for that is because quite often there are commercial arrangements between these entities. For example, if I have a tier 1 carrier, a tier 1 ISP, then that tier 1 ISP is going to have a commercial arrangement about the traffic that it sends and receives from its downstream tier 2. I mean, that downstream tier 2 is going to be paying for that access. Okay, that's how carriers make money, right? They charge for that bandwidth. So that downstream tier 2 pays for that bandwidth and for that traffic, and in turn on-sells that bandwidth down to its local ISPs or to its customers directly. And that particular establishment of that traffic flow between those two is established by a BGP route, but is also then subject to some kind of commercial arrangement, quite commonly a commercial arrangement. So what we want with BGP is we don't want things just to automatically happen. With BGP, we want total control over the process. We want total control over which other BGP speaking routers we establish these peer relationships with. And we also want to have a lot of control over how the traffic flows between those two peers. Okay, now BGP gives us a lot of control. BGP gives us way more control than what we get with an IGP. So because we have way more control, there are additional complexities with BGP that we don't get within an IGP. There's a lot more things that we get to control, to add, to filter on, to use to control how routing information is distributed. So And if we come back to the concept of the fact that if we can control the distribution and the flow of routing information, then that routing information will control the flow of traffic on our networks. Okay, so we could say that we'll control the flow of traffic by controlling the flow of routing information. Okay, so we can focus on controlling the flow of routing information, we will ultimately control the way that traffic flows around our network, which is our goal. It's our ultimate goal. So we have a lot of mechanisms built into BGP that allow us to control the flow of routing information, which in turn controls the flow of traffic. Okay, so let's just get into this a little bit. So we've discovered that BGP is the core routing protocol of the internet. In fact, it's in an RFC 4271, which supersedes the previous RFC of 1771. About 10 years in between those two RFCs. So it's described as a path vector protocol used for inter-domain routing, inter-autonomous system routing. So BGP views the internet as a collection of autonomous systems. Now, we did talk about this a little before. What is an autonomous system? How would you describe an autonomous system? So we describe an autonomous system as a collection of routers that are under the same technical administration. Okay, so my local ISP has their routers being administered by their particular network operations people. Okay, so those network engineers that work for my local ISP look after their routers, and they've got an IGP running on that, which gives them connectivity, and they will then configure their BGP routes accordingly, or peers accordingly. My tier 1 Telstra ISP, well, they've got their network engineers looking after their routers. Their routers are under that particular technical administration. Okay, so the traffic that sort of goes from one to the other is controlled by BGP. The routes that are within the autonomous system are managed predominantly by your IGP. So we looked at the fact that BGP routes between autonomous systems predominantly, and the IGP is contained predominantly within an autonomous system. So when should I use BGP? Well, we've already discovered that an internet service provider will always use BGP because it has to use BGP to gain connectivity to its upstream or downstream peers. Tier 1 ISPs will use BGP to connect with other Tier 1 ISPs, and it is those peering arrangements around the Tier 1s that form the internet backbone. Okay, so BGP is always going to be used by an ISP, by a telecommunications organization. If you are a network administrator, network engineer within a telecommunications company, then you're going to be having to get very familiar with BGP. If, however, you're working for an enterprise, let's look at this customer A here. Customer A has got multiple ISP connections. So customer A in this diagram has got a connection to ISP A and a connection to ISP B. So let me ask this question. Because you've got multiple connections to different ISPs, does that mean that I therefore now have to use BGP to manage those multiple connections? Can I have multiple connections without using BGP? If I didn't use BGP, how would I connect to more than one ISP? Have we looked at anything like this before? So I've got more than one ISP, and I've got connections to both. Do I therefore have to use BGP to manage that? Excuse me. Well, no. It's quite possible to have static routes to both of those ISPs. It's quite possible to set up a situation where I may have a route preference of one static route over the other, so it would be a default static route. I can have a situation where I can have one of those routes as active and one of those as a backup route. That would work. But what if I wanted to actually send traffic to both at the same time? And I thought that either of those particular paths to either of those ISPs was equally as good. Is that possible without BGP? Yes, that's possible. I could simply put in place 2 default static routes, and then I could load balance them, couldn't I? When we talked about load balancing, I could load balance those 2 static routes, quite happily be sending and receiving traffic across those links. So where would I need BGP? Well, there's a few things to think about. It really depends on the size of the organization and the amount of control that is needed as to what traffic flows across those particular links between the customer and the ISP. And also the amount of independence the customer needs as an organization. Okay, let's think about the static route situation that I just described. So if we have a static route, and here's an example down here of customer B. So customer B down here has got just one connection and has a static route. Okay, so think about the IP address that customer B has got configured on its edge router here, the router that connects over into the internet or connects over to the ISP. That IP address, where does that IP address come from? How does it get that IP address? Any ideas? Do we just make it up ourselves, or is it given to us? Say we're customer B. Do we make it up, or are we given that IP address? Think about your internet connection. All right, you've got a public IP address, haven't you? Yes, you do. Okay, you can nod your head. You do have a public IP address. Where does it come from? How do you get it? It comes from your ISP. Exactly, it comes from your ISP. So what happens is that, in this case, ISP B has got a block of IP addresses, which it either got directly from its regional registry or potentially from its upstream tier 1, perhaps. Okay, so basically it's either got it directly or it's got it from its upstream peer. So out of those addresses, it allocates 1 to customer B. Okay, so what happens if customer B, for some reason, decides to change its ISP? What happens? It gets a different public IP address, doesn't it? Okay, different public IP address. So the IP address that customer B has is dependent upon the particular ISP that it is using to connect. Does that matter? Would it be a problem to change that static IP address? Would that cause any issues, do you think? Okay, think about our situation here in ACIT, all right? You guys, we have a public IP address, okay? Now, how does it affect you as students in how you relate to us? Does it have any effect whatsoever on your activities as a student of ACIT? Has anybody ever connected via VPN? Ever? Okay. Did you notice there was an IP address that you referenced when you make that connection? Anyone notice that? Okay, you notice that. Good. Where did that IP address come from? Came from our ISP. What would happen if we changed our ISP? We'd have a different IP address. Okay? So you guys would then go to connect, and that old IP address wouldn't work. Now, not such a big drama. We'd have to say, hey guys, here's the new IP address. All right. Well, that's not so difficult for us to do. We just send you all an email, update information on our websites. Okay, just imagine over here customer A. Just imagine that customer A is the Department of Defense. Okay, quite a big organization. May have a number of different connections to different ISPs. Probably have a lot of external communication that relies on the IP addresses that it has. So an organization like that does not want to be dependent upon its ISP for its IP addresses. It wants to have its own IP addresses that it can own irrespective of what ISP it uses. Does that make sense? It wants to have that degree of autonomy, that degree of independence. In addition to that, so in other words, what we're saying is if it happened to change ISPs, it wouldn't have to change its IP addresses that it used to connect to the new ISP. It would retain that IP address. Why? Because it's not getting the IP address from the ISP. It's getting it directly from the regional registry. Now, you need to be a fairly substantial organization to be able to do that, but certainly can be done. So the other thing is, an organization like that, like the Department of Defense, for example, would want to have a high degree of control over the traffic that went between those two ISPs. For example, maybe that there were certain types of traffic that may need to go across one particular link, and other traffic that may need to go across another link. Maybe you would want to control exactly how that traffic was sent across those links. Maybe you'd want to receive traffic on one link and send traffic on another link, for example. Maybe that would be an objective of that organization. So there are different mechanisms, different levels of control that may be needed. So in that situation where you want to own your own IP addresses, you want to have a degree of control over the traffic other than just, well, load balance or active route, backup route, which is one of the only two possibilities you have if you have static routes. So if you want to have more control than that, then you need to use BGP. So the question is, where would an enterprise need to use BGP? It's when you need to own your own IP addresses and you need a greater level of control over how that traffic goes between those different ISPs. Okay, so we've got these multi-home customers use BGP to control inbound and outbound traffic is kind of the point that we're making here. Okay, so let's look at BGP peers. So what we've already said is that a relationship between BGPs is called peers. So in OSPF, we call them neighbor relationships, but in BGP, we call them peers. So they are a peer relationship. We've already discovered that peers are created manually. They do not automatically, a BGP does not automatically establish peering relationships. They are manually configured, always manually configured. So every peering relationship is manually configured in BGP. So BGP peers can reside in different autonomous systems or in the same autonomous system. Let's look at that idea for a minute. So here we've got autonomous system numbers on these different networks here. Okay, so we've got one over here on the left, AS65501, and what we discover is that particular autonomous system has got a peer to two other autonomous systems. And both of those peers are established by the same router within that particular autonomous system. So it's got one router that is configured with BGP, and that one router has a peering relationship with two other BGP routers, both of which are in a different autonomous system. So it only has one BGP router in there. So when we peer with another BGP router that is in a different autonomous system, that is referred to as an eBGP peer or external BGP peer. Okay, the E stands for external. That is an external BGP peer. So a peering relationship between a BGP router which is in one ISP that peers with in one autonomous system that peers with a router in a different autonomous system is an external BGP peer. Let's take a look at this other autonomous system on top here, AS65502. If you look at that, we can see that there are three routers in that autonomous system that peer with other autonomous systems. So each of those peering arrangements is an eBGP peering arrangement. Okay, so that they are passing eBGP routes. That is an eBGP peering arrangement. However, because it has three BGP speaking routers inside that autonomous system, those three routers also peer with each other. Okay, now they need to peer with each other so that they can advertise the routes that they receive from those autonomous systems to each other. So routes that come in from our first autonomous system, AS65501, are received by the eBGP peer in AS65502. But those routes need to be advertised to the other BGP routers within AS65502 so that when traffic arrives on those routers will have connectivity information for those particular for that traffic that arrives, so that traffic can be routed. So those other routers need to be able to receive BGP advertisements, which means that a peering arrangement is established between all three of those. So each one of those routers has a peer with the other two, okay, within that autonomous system. Each one of those routers, each one of those BGP speaking routers will have a peer with the other, will have a peering arrangement with the other two BGP speaking routers. So it's a full mesh peering arrangement in that situation. Okay. Same goes for the autonomous three other autonomous systems, but because it also has got three BGP speaking routers, they will peer with each other. And that is an iBGP peer. Okay, that's an internal BGP peer. So we've got external BGP peering arrangements, and we've got internal BGP peering arrangements. Any questions? Yeah? Well, eBGP peers exist whenever you are peering with a BGP router in a different autonomous system to your own. Well, no, you don't need more than 2. No. So let's look at AS65501. It only has one BGP router. Okay, that one router has got 2 peering arrangements with different autonomous systems, both. Yeah, so wherever you've got iBGP, you need more than one BGP speaking router. Yes, more than one. Okay, so the point there was what I just said is that each of these BGP speaking routers within the autonomous system have a peer with each other. Okay, and if you look at the diagram here, you'll see that the two edge routers out here on each side are not directly connected to each other. Okay, so the question is, if they're not directly connected to each other, how can they create a peer? Well, in actual fact, in BGP, there's nothing unusual about IGP peering arrangements occurring between routers that are not directly connected. So in that case, we're relying on the IGP that's running within that autonomous system to provide the connectivity between those BGP peers that are not directly connected to each other. Exactly. So what happens is when that BGP router needs to send routing information to its not directly connected peer, what it does, it looks in its routing table for routing information from the IGP for connectivity to that particular peer. And that's what's known as a recursive lookup. So it says, okay, I need to send a route. I've got a connection to this peer. I have a peering arrangement. I'm going to be sending a routing update to that particular peer. I'm not directly connected to it. How do I get to it? It looks into its routing table, which has been populated by the IGP, and finds the next hop route to that particular peer. Now, what these iBGP peers, as we're sort of getting into this a little bit now, these iBGP peering arrangements are established between the loopback interfaces of the iBGP peers. So we actually, and what that means, of course, is that the loopback interfaces must be included in the IGP's routing protocol. So when we're setting up our IGP, you've got to reference the loopback interfaces as part of that IGP. Okay. All right. So that we can get connectivity between them. All right. That's just a fairly standard practice and a best practice in setting up that IGP. All right. So okay. So that was just answering that question as to how do we get connectivity between IGP peers that are not directly connected to each other. Okay. All right. So the note here is that IGP is used because multiple BGP speakers exist. Okay, and we need to be able to share BGP routes from one BGP router in our autonomous system to others. So we need to be able to share those routes, and therefore we create the iBGP peering arrangements. Okay, how are we going with that? So far, so good. Okay, so um, let's talk about a little bit more about these BGP peering sessions. We've already said that they are manually defined. They rely on TCP connections. So what does that mean? Well, that means that we use the TCP transport protocol to establish a connection between our BGP neighbors. We've already mentioned that there's no automatic neighbor discovery mechanism within BGP. We don't want that to happen. We don't want just creating peers with absolutely everybody and anybody. No, we want to control exactly who we peer with and how that traffic exits or enters our autonomous system. We absolutely want to control that. So it's always manual. So let's just go through a little bit about this process of how the peering, the peers get connected. We'll get into the configuration of that later on, but we'll just go through kind of the BGP process here. We start off in idle state, we then go to connect state, it then transitions into active state. The next state after that is a state called established state. So we'll get into this TCP process here. So the first thing is the two peers establish a TCP connectivity. So there are the usual handshakes and so on that go through and acknowledgements that go through with TCP at that level. So we establish that connectivity. Oops. Then let's go back a bit here. Okay. Then with the BGP connectivity, we then go through three states there: open sent, open confirmation, and established. So once the TCP handshaking and acknowledgements have been completed, then the BGP router sends an open message to the other peer. The other peer confirms that it's received the open, and then they transition into an established state. So the established state is the point at which they can now begin to exchange routing updates and other information. Okay, so we've had a bit of a look at BGP. We've looked at our peering, our peer arrangements. What we're going to do next is we're going to take a look at BGP message types and just go through and take a look at the types of messages that BGP exchanges. So these messages are used to establish, maintain the peering sessions. You'll note here that they all use a common header, which is basically always part of every communication. Message types, we've got open messages, we've got update messages, keep alive, and notifications. So once we've got this peering established, these messages can be sent. What is an update message? Well, it includes path advertisements and their associated attributes. Remember we said that we describe BGP as a path vector protocol. Well, what we're going to see is that some of the information that is sent with these updates, with these routing updates, is path information. So we'll get into exactly what that is and where that comes from shortly. So it'll update, we can send these update messages with their attributes. We can also list withdrawn routes that are no longer reachable. So we lose a particular peering arrangement, for example, and then that router may send an update to its other routers that it no longer has connectivity to that peer, and therefore those networks are no longer reachable through that particular path. So what does the what the BGP router is doing, it compares the attributes associated with update messages to select the best path. Okay, now we're going to look at what these attributes are. Okay, we haven't really got into those yet. In fact, all we're saying that BGP routes have attributes. So we're going to get into these, what they are, and how they are used to control what route becomes active. Okay, so let's just take a look at the high-level operation here of BGP. So here we've got customer A. Now, customer A is kind of your regular enterprise type customer, which has got a default route to its ISP. Now that is probably, well, 90% of all enterprises are exactly that way, maybe more. So there we are, we've got our default route, a default static route configured on customer A's edge router to its ISP, and likewise the ISP has got a static route, not a default route, but a static route back to customer A's network. Okay, so any traffic that is received by ISP A for customer A, well, ISP A has got a route, a static route, to direct traffic out the appropriate interface of the appropriate router to reach customer A. So, little note here, customer A is using the 172.20.21.0/24 subnet, which was assigned by ISP A. So ISP A has, from its block of addresses that it has received, assigns a part of that block to customer A. All right, so far so good. We've got some autonomous systems here. We've got ISP A, B, and C. You'll notice that they've all got different autonomous system numbers. We've also got as customer B down here as well, which has got an autonomous system number. So the first thing I want you to note, customer A doesn't have an autonomous system number and all the others do. Why? Why? Customer A does not have an autonomous system number, but ISP A, ISP B, ISP C, and customer B do have autonomous system numbers. Why? Okay, the answer to the question is in order to use BGP as a routing protocol, you must have an autonomous system number. Okay, you must have one. Now, you either get it from your regional registry. In other words, ultimately, all these numbers are managed by IANA, which are delegated to regional registries. So you either get it directly from your regional registry, and that becomes your organization's autonomous system number. Or what is also possible is that if all of your connections are with the same ISP, there is a private range of autonomous system numbers that an ISP can delegate to its downstream customers, a private range. Okay. So for a large organization, like before we were mentioning, say, the Department of Defense, of course, they are going to have their own autonomous system number delegated by a regional registry. Okay, so here we have, to answer that question was, the reason customer A does not have an autonomous system number is because it is not using BGP. Okay, it's just using a static route. It doesn't need an autonomous system number. All right, so let's take a look at how this scenario plays out. So what we've got here in the big blown up section here is a look inside of ISP A's network. We can see that on R1 we've got a static route for customer A. What we also see is that R4 which is a BGP speaking router, is advertising out to its BGP peer an aggregate route. Now, remember we talked about aggregate routes last week? Last week we talked about, you may nod your head, yes, we remember that. We talked about aggregate routes last week, and what did we say? An aggregate route is a block of routes that encompasses a number of contributing routes. So essentially what we've got here is this particular ISP has been given a block of address space, and all it does is it advertises that entire block of address space to its BGP peer as an aggregate route. So it's got the 172.20/00/16. So that's its block of addresses that it has been granted by either its regional registry or its upstream peer, maybe it's upstream tier 1. So it's going to advertise that aggregate route out to its upstream peer. And of course, any traffic that arrives on R4 from those peers, R4 will have the more specific routes to those specific networks, which would have been generated by its IGP. Does that make sense? Okay, so the ISP A's IGP will provide ISP with the specific routes it needs for that connectivity within its own network. Okay, does that make sense? Okay, so all it needs to do is advertise the aggregate out. Okay. This is a really important note here as well on the bottom, is that all BGP routes start as something other than BGP routes. That's an important thing, isn't it? Okay, so what we're saying here is that BGP doesn't go around automatically figuring out routes for itself. No, any route that BGP knows about has come from another protocol. In this case, it's come from an aggregate route which has been configured on R4 by the network administrator and exported into BGP by policy. Okay, so BGP is advertising that route and it's been put in, it's either usually by policy or by configuration, one or the other. What's that? So, what we're saying is that there's an aggregate route configured on R4 which has been advertised by BGP. Okay, so R4 is advertising an aggregate route into BGP. Okay, that's what we're saying here. Okay, and that important point we made is that all routes start as something other than BGP routes. Okay, so they all are put into the protocol by either configuration process or a routing policy process, which essentially exports those routes into BGP. Okay, so let's just go through this process here. So ISP A will advertise the aggregate of 172.20.00.16 through BGP to ISP B. So it advertises it out. What it does when it advertises it out is it adds its autonomous system number to the route advertisement. ISP B will then re-advertise that route, and it will say it's reachable through 65002 or AS65002 and AS65001. So ISP B adds its autonomous system number into the path information on the route. So this is path information. And then ISP C will again add its autonomous system number into the path information on the route. So customer B will receive that route from ISP C. So the thing to note here with this process is that every time a route is re-advertised, the autonomous system number of the advertising router or the advertising AS is added to the route. Okay, so the originating autonomous system, ISP A, puts its AS number on the route. This is the originator, ISP A. B re-advertises, adds its autonomous system. C re-advertises again, adds its autonomous system, and that is received by B. Okay, how are we doing so far? Okay, so what we're adding to the information as it's re-advertised is the autonomous system number of the particular autonomous system that's advertising it. Now, this is path information, the path. That's why it's known as a path vector protocol, because we have path information within the route. Now, that's quite different to how an IGP works. You don't get path information in an IGP. You get a metric, which is a number, and you get a next hop. That's it. You don't get an entire path through which that particular traffic would have to go to get to its destination. So customer B down here knows that to get to, if it has a traffic that has to go to customer A, it has to go through 1, 2, 3 autonomous systems to get there. It knows that information. Okay, so the BGP protocol has a lot more information than an IGP protocol has. So it uses this information to select a best path. Okay, so that's not all the information. That's just a bit. It gets a lot more. We're going to get into that as well. Okay, so customer B advertises its network, being a BGP, having BGP speaking router configured there. Advertises 172.31.1.128/0.0/20. Sorry, it'll advertise that through BGP to ISP C. It will add its autonomous system number to the advertisement. C will re-advertise it, add its autonomous system number. B will re-advertise, add its autonomous system number, and that will be received by A. Okay, so ISP A will receive a route, and it will also receive the path, which is the autonomous system through which that traffic will need to pass to get to its destination, which in this case is customer B. Yeah. All of them. All the autonomous systems. Because that is part of the information that BGP uses to select the best path. You imagine that BGP has to manage routes for every network in the whole world. Okay, the Internet routing table has tens, hundreds of thousands of entries. So that if you took the collective routing table of the Internet, hundreds of thousands of networks. So any particular ISP may have multiple connections, and it's very common that as an ISP you don't just have one peering arrangement to an upstream peer. For example, our local ISP just down the road here has 2 upstream peers with different tier 1s, and in addition to that has other peering arrangements which are not to upstream peers but are through a thing called an internet exchange. Okay, now we'll talk about those later, but essentially they are other peering arrangements that may be beneficial to an ISP. So it may have multiple peering arrangements, therefore multiple possible paths to any particular destination network, and what BGP has to do is decide which of those paths is going to become the active route. And one of the mechanisms, one of the metrics that it uses is the path information. So it's the route with the less autonomous systems in its path is going to be a better route than a route with more autonomous systems in its path. So it's going to choose the best route to any particular destination network. Okay, so and what you can also imagine is that all those upstream peers that particular ISP is connecting with are also paired with other BGP routers, which are also paired with other, which are paired with other, which are paired with other. So there are hundreds and hundreds and hundreds of different routing possibilities that are being advertised and re-advertised, and every BGP router has to decide what is the best path, and then it re-advertises the best path. Okay, so ultimately a BGP router will be presented with many paths to a network, and it then must choose the best. And one of the mechanisms that it uses is how many autonomous systems does that traffic need to go through to get to a particular destination. Okay, it's one of the selection criteria. Okay, what we're going to do, we're going to take a little break there, and when we come back, we will continue our discussion on BGP.